So, I would like to say that we should be welcomed for today in the new topic, which is called, in short, only SEM. We will be using this shortage usually, but this SEM stands for the expression structural equation modeling. So now we are opening the topic of structural equation modeling. And we will try to cover basic parts of structural equation modeling in next 4 lectures. So it will be quite a long discussion about this methodology. So first of all, I would skip into the next slide, and here we have I would say, short list of the literature you can acquire for structural equation modeling. If you would be interested in detailed treatment of structural equation modeling, and if you would like to read the textbook, which is, according to my opinion, something like standard textbooks for structural equation modeling on many universities, so you would definitely take Rex B. Klein textbook, which is called Principles and Practice of Structural Equation Modeling, published by Guilford. If I remember well, currently we have the 3rd edition. This one, 2005, is the first one, but doesn't matter which edition you would get, you would recognize basics of structural equation modeling in very, very detail. Klein's textbook is consisting of something like 400 pages, so it is very, very detailed description of these structural equation models. Quite interesting book can be one of book from series from Barbara Byrne. Here we have the title, which is called Structural Equation Modeling with Amos, but there exist at least 3 more books with nearly the same title, only changing the program Amos with different software packages, UQS, Literal, and M+. So there are 4 books, 4 different software platforms. And according to my opinion, especially these books, structural equation modeling with Amos, M+, UQS, and Literal are the best book for those who would like to practically analyze data and to understand all features of their software package they are using. So I can recommend strongly Barbara Byrne books about structural equation modeling via different software platforms. Then we have 3 titles which are at some, I would call it, elementary or basic level. Maruyama, Basics of Structural Equation Modeling, Krakow, First Course in Structural Equation Modeling, or Schumacher-Lomax, A Beginner's Guide to Structural Equation Modeling. So in comparison with previous, it means Klein book and Byrne books, these 3 books are quite basic level, only for some introduction. And if you would like to read more about the advancement in structural equation models and about special application, so there is a special journal which is called Structural Equation Modeling, and you can find many of articles from this journal online without any payment. So I can recommend you to read these articles in Structural Equation Modeling journal. And now the question is why we should use structural equation modeling and why we are not only continuing previous practice. So we have just covered linear regression, then we have covered logistic regression, then we could cover individual techniques, and now we would like to try to say that everything we have covered in this course and maybe in many previous statistical courses can be given into one big parcel, and this parcel can be called structural equation modeling. So structural equation modeling is something what could be called as general approach for relationships between variables. And it doesn't matter whether our variables are binary, nominal, ordinal, or cardinal. All these can be treated via structural equation modeling and, of course, appropriate estimation techniques. We would mostly cover only discussion about cardinal variables and longer ordinal scales, but believe me that current structural equation modeling can handle all variables that you can imagine in statistical models. So if I rephrase the logic of structural equation modeling very, very briefly, so we can say that up to date, we have covered regression and factor analysis in this course, and structural equation modeling is nothing more than possible combination of regressions and factor analysis. And if I go back to previous lecture about exploratory factor analysis, so we have discovered that we can, in data analysis, use variables that are present in our data matrix. We usually call these variables as manifest or observed variables. So variables that are present in my data matrix are called observed or manifest. And in factor analysis, we try to find something behind my observed data, something behind my manifest variables, and these hidden, latent, unobserved variables were called factors. And in structural equation modeling, this logic could be applied as well. So we can combine in one model variables that are observed, manifest, or unobserved, latent. So that's only a repetition of previous discussion from exploratory factor analysis. And before we start real structural equation models, so it means that the next lecture will be devoted to the first real structural equation model. We will slightly go back to previous discussion about correlations and regressions. And today we will cover the topic of regression and correlation through structural equation modeling approach. So it will be slightly different kind of approach to regression and correlation. And we will learn, I hope so, quite new and interesting stuff. And maybe that you will try to use also for correlations and regressions structural equation modeling framework for future. So that's only the first insight, and we will also try to use these, let's call it simple models as correlation and regression, as you are familiar with these models, so it will not be very difficult to understand basic examples. And we will also learn how to perform structural equation modeling in JASP today. And maybe slightly inconvenient for us would be that JASP in this structural equation model framework is not available through menu. So there are no clicking menus. But it would be necessary, at least partly, to write commands. So we will be using some special programming language, and this language in JASP is based on a well-known package, Lavan, which is in our project prepared for structural equation models. So this first introduction will be also devoted to this Lavan package and its command syntax. Okay, let's start with the first picture. Sorry for my typo, I will check it and change it. Here we have the first two models and pictures that are related to these models. As in structural equation models, it is quite common that we are using not only description of our model by equation or by words, but we are using also pictures. I would start the introduction of this graphic notation in structural equation modeling briefly. And then after this brief introduction, of course, we will switch into real life computations through JASP. So first of all, the first model for which we have picture here, X and Y and double-headed arrow, is the model of correlation. So I would call it that this model is undirected relationship. So there is no direction from X to Y or Y to X, but this arrow goes to both sides. So there is no independent and no dependent variable. Only x is related with y. So this is the information hidden in this picture. And there is one more information or one more important feature on this picture. And you can see here squares or rectangles. And squares or rectangles we are using for variables that are manifest. So it means they are present in my data matrix. So here it means I am computing correlation for two observed variables that are called x and y. So that's correlation model. And before we start to compute anything, it is quite easy to guess that the most important information from computation for this model would be to compute the relationship. It means the value which would be related to this double-headed arrow. So I would expect that the software would compute for me the correlation or maybe more general covariance for these two variables. I would only add one more information, and we would go back to this picture repeatedly, that in structural equation modeling, there is one more computation, which is, let's call it, behind the scene. And JASP or another software package will compute for you also the variance for the first and variance for the second variable. So for example, for this picture, we will be computing three estimated parameters: variance of x, variance of y, and relationship between x and y. So these are three estimated parameters for this model. Previously, if we covered correlation analysis, we expected that we are only computing these relationships. But according to structural equation modeling, we need also to compute the first and the second variance. So you should remember this rule. We will be repeating these rules many times, and I will also add the list of the most important rules in some of the next lectures. So that's the first model, correlation model, and it will be the first model we would cover in a few minutes also by real-life computations. Let's go to the second model, which is very, very close to correlation, and it is simple regression. You can see we have here also x and y, both in rectangles, but there is one or single-headed arrow. Only from x I'm going to y. So it means that x is independent and y is dependent. Sorry for this typo, of course, that y is dependent. X should be correct. So here is relationship. And according to your previous knowledge, I guess you can help me. What should be the meaning? What could be the meaning of this E, which is closely related to y, to dependent variable? What could be this E part of the model? Can somebody help me? What is the meaning of this E part, which is related to dependent variable?
These are the random errors.
Yeah.
These not observed.
Of course. As if we are trying to explain y through x, we will be successful at maybe 20, 30, 40%. But the rest would be, let's call it, unexplained variance. And this unexplained variance, so it means something what cannot be explained by my model, by this independent variable, must be hidden in this random error. So it is unexplained part of the model. Only, I would like once again to add some features. So you can see that these two variables, x and y, are observed variables for this simple model, but this E is unobserved, latent. It is circle. So in the circle, we are using, as we know from previous discussion about factor analysis, so for circles, we are discussing about latent or unobserved variables. And this latent or unobserved variable is related to dependent variable. So it means here we have unexplained variance of the model, and here we have explained part. So once again, we would be briefly discussing about estimated parameters for this model. So I guess that the most important parameter usually would be what is the relationship between x and y. So it means this parameter, and we know that we usually call in regression this parameter as regression slope. So this slope would be maybe the most important. But unfortunately, we need to estimate more parameters than only slope. We also need somehow to estimate variance of this random error plot. So it means of this E as latent variable. If we go back to our previous discussion about regression, so you know that for every regression, we try to compute proportion of explained variance, or in another way, it is called R-square. And this R-square is based on this proportion of unexplained variance, and the R-square is only the rest. So it means explained variance. So this variance for random error is very important for computation of R-square. So that's the first part we need to estimate. So not only slope, but also here we need to estimate variance of this random error plot. And one more feature here will be estimated parameter. If I go back to a correlation example, so I try to discuss that for x and y, as none of these are dependent variables, I must estimate also the variance. And my question is, it is a simple analogy here. So for which variable here, I would need also to compute or estimate variance. It would be x, y, or maybe e. We know that for e, we would need to compute variance. So for x or y, I would need also to estimate variance. Can you help me? Once again, for correlation, there is no dependent variable, and for independence, I must also estimate the variance. So for which variable here I would be estimating the variance?
For x.
For x. Okay, so if I summarize here briefly our discussion, so I would need estimate variance for x, I would need estimate regression slope, I would need also to estimate variance of E, and fortunately, it's not necessary to estimate this relationship, as usually, and most software packages uses this simple logic. This link from random error to y is usually fixed to 1. So this part is not necessary to estimate. So this is the first insight into correlation and simple regression model through pictures and through discussion about estimated parameter. So if I go back here, I would be estimating variance, and relationship. So it means correlation or covariance. So it means 3 parameters. And here it is the same. Variance, and regression slope. So once again, 3 parameters. We will postpone currently this discussion to later slides. And now I will move briefly into maybe more realistic multiple regression case. So let's imagine that my model is including not only one independent variable, as we have here, x, but we have here, for example, 3 independents, x1, x2, and x3. So we are preparing a regression model like this one, and maybe it is the purpose of this picture that some parts on this picture are missing. So if you compare this picture and previous picture of simple regression, can you help me to identify some missing parts in this model? So what is missing on this picture? If I compare to previous one, so this one was
unexplained.
Yeah. Here we should have, of course, some random error part, and here we should discuss about one of the basic rules for structural equation modeling, that if you have some dependent variable, so you must every time assign some random error, as we are not expecting that we will fully cover information or explain information on dependent variable by independent. So random error should be here. Okay, so that's the first what should be present here. And maybe there is also some more missing part. If I go back to this picture about correlation or covariance relationship, so generally in structural equation modeling, it is expected that if two variables are not dependent, so it means they are independent. Next time we will slightly change these terms, but for today it is enough to use dependent and independent. So the assumption in structural equation modeling, general assumption is that these two independents or more independents are related. So according to this assumption, what could be missing here also? What could be also added to this picture? So once again, the assumption here is that if I have two independents, they should be related. So what could be here added to this picture of multiple regression? What should be the analogy to correlation model here in multiple regression case?
Maybe correlation arrows for independent variables.
Yeah, there should be one arrow, second arrow, the third arrow. So it means that in structural equation modeling, it is usually expected that independents are related to each other. So only if I go back to previous discussion about estimated parameters, so here we have 3 regression slopes. I would also add random error, so I would be also estimating variance for this random error. I would be also estimating variances for this x1, x2, x3, and I would be also estimating these individual relationships as we have just discovered. So this is only a brief introduction. And now it's time that we could switch into JASP, and we could start to compute our results. But before we start structural equation modeling via JASP, so I would first of all compute our result. So it means results for the first task, it would be correlation. Classical way, so it means we would be using procedure for classical correlation, and then we would switch into structural equation modeling part. So here we have only description of our first task. So we would start first of all model for correlation, and we would compute not only basic model, but we will also learn how to test special value of correlation. So we will learn how to test some special values such as 0.4, 0.5, it is expected according to previous results, and I would like to know if still my results support thesis that correlation is following this pattern. Once again, before we start, we would compute classical correlation stuff. Here I have a data matrix which is called SEM Reg Core, and it is including only 4 variables called WB, DAP, SS, and PC. And I would add meaning to these variables. We will be using this data file also next lecture. The first variable, this shortage WB, stands for well-being. So it is measurement of well-being of a student. These data were collected on university students in the Czech Republic. The second variable is based on measurement of depression, so well-being, depression, and 2 next variables are social support and proactive coping. So here we have well-being, depression, social support, and proactive coping. And first task we will try to cover would be the discussion about relationship of well-being and depression. And once again, before we start any real computations, it would be good to get some idea what could be my result. So my question to all of you is what is expected relationship for well-being and depression? Do you expect it would be positively, negatively, or even not correlated at all? And if positive or negative, would be this correlation strong or weak only? So if you can help me, I would be happy. So what's your expectation about relationship between well-being and depression?
I suppose there will be negative relationship. The higher well-being, the lower depression.
Okay, so it seems realistic. And do you expect that this relationship measured by correlation coefficient would be strong or weak?
I would say weak because there are more factors that go to this problem.
Okay, so thanks a lot for this first insight. And I would like only to repeat that if you would like to compute correlations in JASP, you have 2 options. You could go into descriptives and use graphic tools which are present here. An alternative option is that you could go also to regression and here correlation. So I would choose regression and correlation. So I would go back as I have prepared all this step. And you would take these 2 variables, so it means well-being, WB, and depression, and go to variables window. And if I would if I would like to get more results, so please ask for confidence interval and ask also for plots, scatter plot, densities for variables, and statistics in the plot. So here we have the basic results. And before we start to read pictures, I would go into the table. And here we have our results. And according to my computation, Pearson's correlation, which is default, of course, you can change this default into Spearman or Kendall's coefficient here. But according to my result for Pearson correlation is minus 0.62 if I slightly round up. So first of all, we expected that this correlation would be negative. So it's valid. We also expected that this relationship would be weak. So according to my opinion, this correlation is quite strong one. This is first result. It seems to me that depression and well-being are quite strongly correlated to each other, at least for these data. And once again, these are data for Czech students. So this is the first insight. If you would like to see graphically our results, so you can see histograms for well-being and depression. And also you can see our correlation plot here, and there is also imposed line, which is describing this negative relationship. And here we have once again correlation coefficient and also 95% confidence interval. This confidence interval is also included here in the table. So these are first results for us. So we know that these two phenomena are quite closely negatively related. So that's correlation or classical correlation. And if I would like to add structural equation models, there is first necessary step into JASP. You must go into this blue plus symbol on the right upper corner. And if you click here, you can add some procedures into JASP. And the procedure, which is easy to guess currently we would need, is structural equation modeling, so SEM. So I would click here. And you can see that immediately JASP is including SEM here as the last menu item. So here we have SEM option. And before we start to compute this correlation model, we would need some more information how we can prepare such model in JASP. So I would switch once again into the presentation. And this slide is describing basic language features in JASP, or let's call it a different way. It is originally from Lavaan package, which was prepared for our project. So for today, we would need rules how we can describe correlation or covariance. And this rule is very simple. You take two symbols, let's call it simply waves, or in programming languages, we usually call this symbol as tilde. So you can take these two tildes, and by this expression, you would say to JASP, okay, I would like to compute correlation or covariance. So it means a relationship with double-headed arrow. So this is the meaning of these two tildes. These two tildes means there is one and second arrow. So double-headed arrow is expected. If you would like to compute regression, this would be our second model today. There is a different style of expression. So you would say which variable is dependent. For example, y is dependent. Then one tilde, as it is one-headed arrow only here, as you can see. And then you would use nearly the same phrase as for regression equations. So it means the first independent variable plus the second, etc., etc. So this is the style for regression modeling. So for regression, one wave or one tilde. For correlation, two tildes. And later, we don't need it today, but later for confirmatory factor analysis, we would also recognize there is one more symbol, which is equality sign and one tilde. So we will apply these symbols for confirmatory factor analysis. So we would need it today. So that's only how we can prepare models. And for your easy preparation of the model, you can use this presentation, and these tildes are prepared for copying for you. But usually you can use, of course, tildes on your keyboard. It is usually left upper corner of your keyboard with English symbols. So you can use it, of course, also without copying from the presentation. So now we would switch into structural equation model option. So I would go into JASP, SEM, and the first one option, which is called simply structural equation modeling. So if you click into this option, I would say this is something like mixture between writing of commands and between menus. Here you have big window, which is expecting that you will type some commands. It is written here, enter Lavaan syntax below. So here for this big window, I am expecting to write something. And then there are some options like in classical menus such as statistics, options, and advanced. We will be using these. But first of all, we need to use this window. So you must click into this window and you must prepare our model. And I must go back to variables and I would like to make relationship for well-being and depression. So I must recognize that well-being variable is called WB, warning with small letters. Small letters and big letters are different symbols for R. So that's why it is also different symbol for this structural equation modeling dialog. So I must type here WB, then double tilde and DEP for depression. So here I would type WB, then double tilde. So I would change out my keyboard from Czech into English. So one tilde and the second tilde and DEP. So only for your possibility to check this model. So I would click here and I would type here this model which we are currently computing. So this WB, small letters, tilde, tilde, DEP, it would be our model. Before we run this model, you can check here that Control plus R is for running the model. I would go into some advanced options. So please click into statistics. And first of all, please ask for so-called additional fit measures. Next, you can go into options. I guess we don't need any special options currently, so we can skip this and go into advanced. And I guess that for this advanced, you can only ask for the picture, which is path diagram. So it means that JASP will prepare for you some picture that would be similar to this picture. So you can ask for path diagram. And I would only click once again into statistics, as I guess that there is some option slightly down for standardized results, or calculation standard. It seems it would be default, so we would need any other option currently. So here we have for statistics additional fit measures. And for advanced, we have asked for path diagram. So now we can go back to this dialog and click Control plus Enter. So JASP now needs to compute our results and prepare pictures. So you need to wait for a minute, I guess. Still, I do not have results here. I hope that your computers are faster than mine. So still I'm waiting here. Can you see results on your computers currently?
Yes.
Okay, so maybe we need to wait for my computer as it is quite slow one. But I guess that we can start discussion about results. And first result that you can check, I don't know why my computer is still not computing, you can find in the table which is called parameter estimates. And here you can find in standardized all option the value of the correlation. So now my computer is picking up, so it seems we will get results. So for this column standardized all for parameter estimates, you should see the same value of correlation as we have previously discussed. So it means it would be minus 0.617. So I guess that we have also results on my computer. So here is the correlation. So we should recognize that for structural equation modeling, correlation is called as standardized parameter, standardized covariance. Before we would go further, I would like to repeat only basic formulas that can be useful for better interpretation and understanding of structural equation models. So here I have two well-known formulas from classical statistics. So the first formula says that so-called covariance, so it means general measurement of relationship, which is from minus infinity till plus infinity, is computing as you take individual differences for the first and the second variable from their means and multiply these and then divide by the number of units minus 1. So this is computation of so-called covariance. So it is general measurement of relationship, especially linear relationship for variables. And once again, values of covariance are from minus infinity till plus infinity. So I would call it in structural equation modeling, this covariance as unstandardized coefficient. If I go back here to my result, this covariance for my data, it means well-being and depression is minus 0.108. So if I would apply this formula into my data, I would get this result minus 0.108. But the problem is that it is quite difficult to interpret this unstandardized coefficient or covariance. Once again, it is from minus infinity till plus infinity, and nobody knows whether minus 0.108 is big value or small value. And that's why statisticians decided to somehow recompute covariance and standardized covariance. And here we have the equation by which we are applying this recomputation. So we take covariance value and we divide this covariance by standard deviation of the first variable multiplied by standard deviation of the second variable. So correlation, Pearson's correlation, is nothing more than covariance, which is standardized by division of two multiplied standard deviations. If I would go back, it would be also possible to compute it here directly, as here we have covariance. It means WB tilde tilde deb is covariance. And I have also WB tilde tilde WB and deb tilde tilde deb. So it means this is variance of well-being and variance of depression. As I expected, 3 parameters are computed here. So it means variance for X, variance for Y, and relationship. So that's why this table is including 3 rows. Relationship, variance, variance. And if I would take this covariance and divide it by square root of this variance and square root of this variance, these together multiplied, I would get this standardized value of correlation coefficient. So once again, for structural equation modeling, for relationships with double-headed arrows, these values, which are estimated parameters, are unstandardized or so-called covariances. These standardized values are correlations. And recomputation by standard errors or variances is possible. So that's the first information we can cover here. The second information, which is important here, is the information about this result. So we have just discovered that this result in this structural equation modeling is all the same as previous result in classical statistics. So you should remember that if you are applying correlations or covariances by structural equation modeling with no other added information, you are just describing your data. So you are computing your relationship by correlation or covariance. You are describing your data by variances and nothing more. So this is only descriptive model. If I would like to add something more, I would need to add some more tricks we would be discussing in a few minutes about fixing. And one more comment which is necessary to add to the evaluation of structural equation modeling is based once again on previous picture. So once again, if I go back to my picture, so I'm estimating one and second variance, so two variances, and this relationship, so it means covariance or a computed correlation. So three pieces of information are estimated. And the question is, how many pieces of information I have at the beginning? So it means how many different pieces of information I am using for this computation. And that's quite easy. Here I have variance of X, which can be computed from my data matrix. I would go, for example, into descriptives and compute variance, or I would go into structural equation modeling, and here I have variance for well-being. Here I have variance for depression. So this is also something what could be called as input for my computation. And the second, the last one part which is available for me if I have two variables in my data set for which I am using data analysis is that I can compute also relationship for these two. So from variance, and relationship, I'm computing variance, and relationship. And that's why I'm using all this information and I'm only performing descriptive statistics. In another way, I would like to say that the difference between input, so it means three pieces of information, and output, once again, here three pieces of information, is called degrees of freedom. So here I could go into this table, which is called chi-square statistics, or the same can be also found in the third table, which is called model test baseline model. And here you can see degrees of freedom, which is once again the difference between input, number of pieces of information I have, and number of pieces of information I would like to get. And this difference here is 0. And if degrees of freedom is 0 in structural equation modeling or in statistics generally, there is no option for statistical testing. So if I have 0 degrees of freedom, so it means I'm using maximum amount of information for maximum amount of estimated parameters, I'm not able to testing anything. You can check here that here would be classically p-value. So it means p-value for evaluating of some overall chi-square test, but here there is a blank space. So nothing can be tested for this model. So if I'm estimating classical correlation, you will see the same task for classical regression. There is no option for testing such a model, and this model is only a descriptive model for my data. And now we will learn how we can slightly change these settings and how we can somehow test model with correlation or covariance in JASP or in structural equation modeling framework. But before I start, you can check here the picture for well-being and depression. If you would like to change this picture, you can also click here and the picture would show you the value of the correlation. So it means standardized parameter. So I guess that after some seconds, JASP will recompute the picture and you can see here minus 0.62. JASP is using here the same style of notation as for exploratory factor analysis. So it means red lines are negative values and green lines are positive values. So this is a picture for our correlation model. So here we have the first model. So I would only change the title. So it would be correlation via SEM. And now I would go to nearly the same model. So I would make a copy of the previous model. I will only ask maybe not to show the picture as it takes memory and it takes time. So I would close this path diagram. And I would only add some condition some fixing of parameters we would add. So maybe that I am using these data for Czech students, and I know from previous studies that the relationship for well-being and depression can be approximately 0.6. So now I would like, instead of to describe my data and describe relationship, I would like to test hypothesis that this relationship for well-being and depression could be 0.6. So if I go back to slide number 6, so here is description how technically we can perform such fixing in JASP or through Lavan language, which is implemented in JASP. So if I like to fix parameter on some special value, such as, for example, value of 6, I would type y tilde tilde 6 times x, and it means that covariance would be the value of 6. Here we would like to fix the value of correlation at 0.6 this minus, as we are expecting negative relationship for well-being and depression at the value of 0.6. Unfortunately, it is impossible to type here the value of correlation, but I must type here the value of covariance. So first of all, I must somehow recompute the correlation minus 0.6 into covariance. It would be quite easy, I guess. If I go back here once again to these equations, so I would like to compute covariance from correlation and standard deviation. So it means that my formula would be, I can maybe type it here. So I would I would be computing covariance as correlation multiplied by standard deviation of x multiplied by standard deviation of y. So I would need only to take correlation, expected correlation 0.6 with minus, and then multiply by standard deviation of x and y. So I would apply this formula and recompute covariance, and then add this expected covariance here, and I can evaluate this model. So we can start this computation. So I would use, for example, Microsoft Excel environment for this computation. Maybe for simplicity, I would copy the formula which I have just prepared to see it in Microsoft Excel. So I will type it here, make it bigger. So here it is. Maybe I can close this dialog for Microsoft Word, not to take memory. Oh, once again, save. So here we have the formula. And once again, I would like to have correlation such as minus 0.6. The question is, what is standard deviation of x and standard deviation of y? So I can go once again back into previous computation. And here we have information about variance of x and variance of y, 0.226 and 0.136. So I'm typing 0.226 and 0.136. So these are variances. And if I would like to take standard deviation, I need to compute square root from this and from this value. Sorry for inconvenience that I'm using here Czech version of Microsoft Excel. For English version, the function for square root will be called sqrt. Here it would be called in Czech language, so it means odmocněná. So I would type odmocněná. In English Excel, you would type square root, or you can use a calculator on your mobile phone. So I would take square root of this value and square root of the second variance as well. So square root for the first variable is 0.47539, for the second 0.36878. And now I will only apply this formula. So it means correlation, this value multiplied by this value and multiplied by this value. So here I'm computing covariance. So here it is. So I'm typing this value multiplied by the first standard deviation and multiplied by the next standard deviation. So here it is. And it says that if I would like to test correlation of minus 0.6, I should test the value of covariance of minus 0.10519. So I would slightly maybe round up. So I would take 0.1052 with minus. So here it is. So I would go once again back into JASP. And here after WB tilde tilde, I would add minus 0.105 multiplied by depression. Once again, I would copy these symbols here. So here it is. So that's my model currently. I hope that this would be correct decimal symbol. If not, just will warn me, I guess. So we can check it. So you can once again click into Control and Enter. So it is incorrect. Sorry for that. So you must replace a symbol for decimal. So here there is a comma. So minus 0.52. Once again, Control and Enter, and now it works. So JASP will recompute our results quickly. I hope so. So before JASP will start, I can only close my Excel here. So here it is, and here we have results. So before we start to read results, we can check that JASP is following our command. And our command was, I would like to take covariance as 0.1052. So you can go to the line with parameter estimates, well-being tilde tilde depression, and it is 0.105, and 2 is missing here as we are using only 3 decimal places. We can check it by preferences, but that's not necessary. You can also check that standardized value, which is approximately the same as we expected by our hypothesis, is minus 0.6089. So it is approximately 0.6, only small differences based on our previous rounding. So we didn't apply precise value of covariance, but only slightly rounded up. So that's the first. And you can also see that here Z and P is missing. So it means that we were fixing this value. So it means the JASP is not estimating this value. We first JASP that covariance or correlation would be like these values. So these values are not estimated. So only well-being variance and depression variance are estimated here. So only 2 parameters are estimated here. And if I go back to our presentation from previous discussion, so we said originally we have 1 variance, 2nd variance, and relationship, 3 pieces of information. And currently we are using only 2 from these 3 pieces of information. So 3 minus 2 is equal to 1. And that's why degrees of freedom for this model is equal to 1. So here there is a space for testing. So here I can test this model. And now I would add some comments about the meaning of this chi-square test, which is applied in structural equation modeling. This test is based on following set of hypotheses. Null hypothesis says that our model is good. That can be very, very simple interpretation, or in other words, maybe statistically more correct. This null hypothesis says that covariance or correlation matrix based on my data is nearly the same as covariance or correlation matrix as is designed by my model. So it means that my model fits to my data. This is the meaning of null hypothesis. An alternative hypothesis says, no, my model doesn't fit to my data. It means that correlation or covariance matrix from my data is quite different from correlation matrix or covariance matrix, which is based on my model. So once again, null hypothesis says model is good. Alternative says no, the model is not good. If we go back into this discussion, what would be nice, to reject or not to reject null hypothesis?
Not to reject.
Not to reject, so it is quite opposite to classical style statistical thinking, and mostly we would like to reject, but here we would like not to reject, so it means not to reject our model, in other words. So let's go to the evaluation of this first test. So we have here degrees of freedom, which is 1. We have the value of chi-square, which is 0.117. This chi-square is test criterion for this test, and it is measuring the difference for covariance or correlation matrix from my data and from my model. This value is quite low one. If you go back into your previous statistical knowledge, you know that normal distribution, classical quantile, which is 97.5, is 1.96 or 2, and chi-square for 1 degrees of freedom is nothing more than second power from this normally distributed variable. So if you take the second power for 1.96 or 2, you have the value approximately 4, or slightly more precise, 3.84, and that is quite below this value. That's why p-value here is quite big. So my question once again is, if we reject null hypothesis here or not, if our model is good or not.
It is good.
It seems that we are not able to reject null hypothesis, so we are not able to reject that our model is good. Yeah, it would be good interpretation. So this is the style of thinking in structural equation modeling. So we have some idea about the structure of relationship. Here our idea once again was that correlation for well-being and depression is approximately minus 0.6. And we are not able to reject such idea by this testing. I would add some more comments to results here, as usually, and we would find these, let's call it unpleasant property of chi-square test. So usually this chi-square test for some real life complicated models is not very useful, as it is very, very sensitive to sample size and also to complexity of the model. So usually we wouldn't be able to conclude about our model by this chi-square test statistics and p-value, and we would need some alternatives. And these alternatives can be found here in the table, which is called user model versus baseline model, or there is also one more table, which is called root mean square error of approximation, or another table, which is called standardized root mean square residue. And there is also one more table, but we would skip this table, which is called other fit indices. So now I would briefly discuss about these results. And I would give you some guide how we can evaluate real life structural equation models. So here from the first table, which is called user model versus baseline model. So it means I'm comparing my model with some predefined so-called baseline model. We are using mostly first two statistics that are called CFI, the meaning is comparative fit index, and Tucker-Lewis index called as TLI. These values are designed usually from 0 to 1. As you can see, TLI can slightly exceed 1, but only slightly. And recommendations related to these fit statistics are following. If these values are approximately 0.9 or higher, so it is a symptom or maybe a small recommendation that your model could be useful. So the values of CFI and TLI above 0.9 are taken as some benchmarks of the quality of the model. So the values should be at least 0.9. This is very simple recommendation we can take in this first step. So here, as you can see, CFI is 1, TLI is even slightly above 1, so it seems quite good for this first insight into the evaluation. Once again, for this correlation model, we don't need these CFIs, TLIs, or other fit indices. Here we can use also the test, and this test says, okay, your model seems good. But here we are describing also more general tools for structural equation modeling. That's why we are discussing also about CFIs and TLIs. Also, for nearly for all the rest of these coefficients, the same logic is applied. So it means they are designed from 0 to 1, and the higher the value, the better the model is. Okay, let's go to the opposite side of the evaluation of structural equation modeling. And the next two tables, root mean square error of approximation and standardized root mean square residuals, try to describe something what I would call generally as mistakes in your model. So this RMSEA and SRMR statistics try to discover whether there are some problems in your model. Once again, these criteria are designed from 0 up to 1, but the logic is quite opposite to previous. So it means the bigger the value, the worse the model is. So RMSEI usually, if we take a classical recommendation, should be below, and there are differences between different recommendations, but usually the recommendation is 0.08 or lower is good for your model. So here we have 0.000, so there are no doubts about the quality of the model according to RMSEA. SRMR is another statistics, the same style, and recommended cutoff below this cutoff, we should get the value for my model is 0.05. Please don't mix this 0.05 value with classical value for statistical testing. Here, SRMR is nothing what is tested. This is only criteria. So SRMR below 0.05 is recommended cutoff. So according to all of these, SRMR, RMSEA, and all the rest, such as CFI, TLI, our model seems promising. So once again, if I slightly summarize up what we have just covered, so I would go back here into the slide number 10. So if I have some expectation about the relationship based on correlation or covariance value, I can, through SEM, test this value. If I take the model with no such fixed value, there is no option for testing or evaluating such model, as this model is based on 0 degrees of freedom, and there is no space for testing or evaluation. And once again, I would like to repeat that so-called unstandardized results, so it means these in column called estimates, are covariances For standardized results, we are using correlations. Mostly, it is more common to discuss about correlations. That's why we are usually reading results in standardized column. Standardized all is the best one for us. So that's all for today about correlations and covariance through SEM framework. So I would stop sharing and